Good. So today we'll go over that. We're going to go over the last one that I didn't go over because I just graded it yesterday. So I'll go over both of the homework sets, and that's really, since those comprise a huge fraction of the stuff that you've done, that's going to comprise the bulk of our midterm review. And then after that, after we get through those, I'll go through what I think you should study for the midterm. And I'm just going to throw up the slide decks and kind of skate through them and make notes on the board. I intended to do that before I got here, but I ran out of time, so here we are. So you guys can watch me do studying for this class, and then you can go study. Backing up to weeks ago now, homework that was due well before spring break, and then there was another homework, and then we did cosmology, and then there was a spring break, and then there was another homework. So this has been a minute, but it's worthwhile. It's good to go through all this stuff again now because there's a midterm on Thursday. Okay, number one, define the local standard of rest, and how does the sun's velocity relate to it? And this has never happened. None of you actually gave me this number. Because I don't know, the question must read weird this year, weirder than it did last year. I was looking for two pieces of information. The local standard of rest is a fictitious rest frame on a circular orbit at the solar radius. That's the important thing. One, it's a fictitious orbit at the solar radius. And that's the important bit. It's not the average of the stars. It's not the motion of the sun. It's, in fact, decidedly not the motion of the sun. It's a reference frame in the galaxy. And the sun's velocity is this number, which is in the book. -10, so it's going down. That's inwards at a velocity of 10, and radially it's a little quick, and it's moving a little down. So I probably need to ask what is the value of that, but that's all right. Does anybody have any questions about local standard of rest? What it is, what it means? Everybody happy with that? Fundamental plane versus Faber-Jackson. Oh man, does it just randomly say dispersion here, or is that a glitch that showed up when I was tweaking them? Huh, hard to say. I'll fix that later. That's the thing I need to talk about. I'll just let you guys answer. So what's the difference between fundamental plane and Faber-Jackson? Let's start with a simpler question. What's Faber-Jackson?
It's a relation between luminosity and the velocity dispersion.
For what kind of thing?
Elliptical.
For elliptical galaxies. So it's a relationship between luminosity and velocity dispersion for elliptical galaxies. Why is fundamental plane, and what then is fundamental plane? Same thing. But fundamental plane also includes the central surface brightness, so it's more what? Accurate. So it's a more accurate model. So there's one thing that I want to talk about here real quick, because this is it's a little source of confusion, not a huge thing, but I realize in this section, we use dispersion to mean two vastly different things, and it's the language that the book uses, and I can tell that that's how the book uses it by the way people answer the questions. So dispersion is spread. It's spreading out of stuff. So there are two kinds of dispersions that we're worried about when we're talking about fundamental plane or Tully-Fisher. Well, actually not so much Tully-Fisher, really fundamental plane. So there's the dispersion of the velocity, and that's sigma v, and sigma v goes like a luminosity to the quarter power. And this is the integral of the velocity of each star minus the mean velocity squared times the distribution of stars, dV. Or I could just say d cubed x. I can just integrate over all space rather than velocity. I can just change what I'm integrating. So it's just the velocity minus the average, square that. That's the velocity dispersion. Sigma squared equals that. The other thing is the dispersion in the plot itself. And there, here he's talking about, what we're talking about, let's do this a little better. So my plot is the log of the velocity on the, let's write that upright. Log of the velocity on the horizontal axis and say the luminosity on the vertical axis. The dispersion is the spread of points away from this line. So there's two kinds of dispersion that we're talking about. One is what the population of stars is doing in the galaxy, and the other one is the spread around the line. So the spread around the line gets smaller. So we're talking about the dispersion of the dispersion. So dispersion is showing up in here twice. Once is in the spread in the graph, and once is this actual quantity that we're looking at. So the important bit about fundamental plane over Faber-Jackson is this second dispersion is what gets smaller. So fundamental plane looks like that, or Faber-Jackson looks like that. Fundamental plane looks like this, where all the points are a lot closer to the line. So that means that the line is a lot more useful, because then when I say the luminosity is my fiducial luminosity times V over V naught to the fourth, I know that this line, in log space it's a line, I know that this line is an appropriate representation of the actual luminosities that I get if the dispersion in the plot is low. Does that make sense? A tale of two dispersions. And I don't think nobody got anything wrong on that. I could just tell that that's a thing that I need to spend a minute on, because people are kind of jumbled up when they're talking about which dispersion. It's not a huge deal. I just wanted to say it again. Okay, classify all these galaxies. Let's make this big. So what's this guy look like?
Non-barred spiral.
It's a spiral. It's not really. It doesn't really have a bar. Kind of has a ring. Does that look like an A or a D? Maybe that's a B. So the arms aren't real tight. They're kind of fluffy. So this is an S. This is an AB, because if you squint, there might be a little bit of a bar here.
Very faintly, yes.
It's kind of faint. Maybe it's there. Hard to say. Maybe there's a bar. So this AB denotes that there kind of is a bar. A denotes that there is not a bar, and B denotes that there is a bar. R is for ring, and then BC describes the bulge to disk and the light ratio. This one here, how about this guy? This one has a bar. It's a very clear bar. It's long and stick shaped, and the arms are a little bit more open than this one, and it's not quite as fluffy. So this one is a B, and it also has a ring. How about this one here? What's that? That's an elliptical. That's the flattest elliptical that I could find. That is an E6. How about this one?
Spiral.
It's a spiral.
With seemingly no bar.
No bar.
And
not much of a bulge either.
A ring? I don't know. I can't really. It looks. That might just be a bulge.
Yeah, there might be a ring there. There's really not a very strong bar. So that one's a B, or a strong bulge. So that one's later type because there's not a big bulge. It's a BC. And then what's that?
What's the RS?
So either there's a ring, or it's S-shaped, or maybe there's a ring, so it's RS.
But what does the C stand for? All the way down.
This?
Like BC.
So the way the way this taxonomy works. So, square brackets. It always starts with S. And then there's an A, B, or an AB. And then there's R, S, RS, for whether or not there's a ring. This one has to be capital and it comes second. This one, it doesn't really matter where it shows up. And then there's the lowercase letter A, B, B, C, 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 D. So you could be an A, an AB, a B, a BC, a C, or a CD. This is a way to quantize things into a continuous thing in a dumb way. So this BC means it's somewhere between a B and a C. Yeah.
So S just means there's no ring?
Yeah, that's right. That's right. So there's a ring, not a ring, maybe a ring.
What does the C stand for, like, physically?
Was that?
The C, what does it stand for, like, physically?
What do you,
Like, how...
Like, what is the scale based on?
Yeah, like, what's the A, B, B?
So, okay, so it's based, so there are a number of things that are correlated with this. And the most important thing when people are quantifying it is the bulge to disk ratio. So that's the thing to keep in mind. If you're like, I can't tell what that is, look at the bulge to disk ratio. If there's a huge bulge, then it's like an A type. And if there's not a huge bulge like this guy, it's a C type or somewhere in there. And I'm not going to be super picky about A, B versus C because it's hard to do by eye. And our last two, where are they? There they are. How about this one? Real strong bar, two real big defined arms, real fat bulge. That is an SA, is an SBA. So this one was the fattest bulge that I could find. So you see how this one is a real bright round thing in the middle, and then it's got its arms, and the arms are not real. The arms are not real kind of fluffed up. They're nice and clearly defined. Yeah.
So is the bulge to disk ratio about size or brightness?
Brightness. But those are related. And then this last one.
Elliptical.
This is God's flashlight. This is the roundest elliptical I could find. It's an E0.
So is that like with no outside, it's just like only bulge, or is there more outside of that? It's just like one just spot of brightness. Is there more?
It's more than a spot though. Those are points. This is extended.
Oh, okay.
Yeah, it's just a big round sphere of stuff. That's it.
Like
And so now, okay, if you really want to dig into all the substructure of this big ass round thing, then yeah, there's some extended halo and some substructure in there and whatnot, but it's all like way, way, way secondary to it's a big round object.
Is it like super dense? Oh, sorry.
Oh, no worries. Yeah.
For the elliptical scale, is it from 0 to 7 or 0 to 6?
I think it goes to 7. And you were saying, it's dense enough that it just looks white in this thing. But if you actually tried to resolve all the stars, you would see stars in it. Yeah. I can find better pictures of all of these. But, okay. And I have to do good time management today because I have a lot to get through. 8 properties that vary along the sequence of spiral galaxies from early to late type. So bulge fraction decreases with type. So in A-type galaxies, the bulge fraction is large, and in C-type galaxies, it's small. The mass doesn't vary a ton. The central brightness doesn't vary much. The physical size doesn't vary a ton. But the bulge fraction changes. The central brightness doesn't change. Oh, I said that twice. The rotation rate decreases with type. The opening angle increases, so A-types have tighter arms. The BV color gets bluer with the later type galaxies. The infrared increases, more dust in the in the later type galaxies. The gas fraction increases with later type galaxies. The fraction of gas that is molecular decreases with type. The clumpiness increases and the globular cluster count increases. There might be another one in there, but a lot of these indicators. One of the reasons that I asked this question is a lot of these indicators are really indicators of passive evolution of the galaxy. And this is something that I really should have spent a minute on already, but I'll do it now. So I'm going to talk about galaxy evolution for like 9 seconds. We'll talk about it more later when we do clusters. But how do galaxies evolve? There are two kinds of galaxy merger mechanisms. There's passive mergers, and this is the star formation. Star formation eats all the stuff. And all of the everything else that comes along with star formation. So star formation is a dominant process in galaxies. I'll touch on what this means in a second. But all of these processes are evidence of star formation burning up all of the gas from the SC galaxies to the early type galaxies. So secular evolution goes up this early to late type classification. So a lot of these are evidence of star formation. So the B to V color, the gas fraction, the molecular fraction, the clumpiness, the infrared light, and the disk to bulge ratio. There's more light in the disk because that's where the star formation is happening. Whereas in a later galaxy, there's not as much star formation in the disk, and the bulge is a lot more prominent. So there's passive evolution, and there's we have dynamic evolution as well, and this is mostly mergers. And we'll talk about stripping in a second, but I'm just going to put wind here, but that's not, we'll talk about that in a minute. But basically, galaxies all started off in the early universe as tiny little things, and they all merged together in this hierarchy of mergers where little things eat each other, and then bigger things eat little things. So there's two types of galaxy evolution, and all of these things are really aiming at passive evolution. The dynamic evolution you can see in other effects, but we haven't talked about that as much. Does that make sense? Do you have any questions about? That's a huge topic, so I want to manage my time a little better. Which we on 4? No, we're on 5. Boop, 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 boop. Okay, so figure 4 shows the rotation profile for this galaxy. It has an inclination angle of 77 degrees and apparent magnitude of 10.4. So I asked 2 questions: what's its max rotation rate? And 2, how far away it is. So we can estimate the maximum rotation rate by looking at this. Think about this as a histogram of the velocities. So most of my velocity is sandwiched between these two extrema. So I just take the left minus the right, divide by 2, and that gives me the rotation rate. I divide by 2 times sine I, and that gives me the rotation rate d projected. That makes sense? So I got my galaxy, I got gases going this way, I got gases going this way. Here's me, here's my histogram. So all the gas that's coming at me is over here, all the gas that's going this way is over here. The rotation rate that I want is just one of these, and I have this inclination angle. So V max is the width divided by 2 sine I, where I is the inclination angle that I gave you. Yeah.
Can you like show the why that's cool?
Yeah, why it's sine I?
Yeah.
So a galaxy is like this. This is the normal vector, sticking out the front. Normal vectors always stick up the front. That's how normal vector works. And it's the angle of that relative to the line of sight. That is this angle I that we're measuring.
Okay.
So when, here's me, when this angle is 0, I just see the face of the galaxy, and I can't see any of the velocity, because all the velocity is in this plane. So I measure the velocity to be 0. It's all just bulk motion. Whereas if the galaxy is like this, it is a normal vector, and here's v. My velocity is like that. I see all of it, but if I'm at an angle like this, then what I see, I need to move myself. The velocity is in this direction. This is vx, and this is v y. What we want is vx, and what we get is the angle of this relative to the line of sight, which is the same as this angle, and no, it's the same as this is the same as
I think that was the right one.
yeah. Well, now I get a cosine.
Yeah,
I think it's 1990.
No, it's not. It's sine. I just gotta draw the right picture. So, what angle is that?
90.
90. I hate getting things wrong in front of people.
Well, that makes sense because it's 1, right?
I think the
Yeah,
way you
sorry, thank you. Sine of 90 is 1.
Okay.
Sine of 90 is 1, so that's all of it. Sine of that one is 45, so you want to go part of it. Make sense? Okay, I'm going to stop drawing pictures or I'm going to screw it up again. Okay. Oh, okay, so then we get the rotation profile, and then what do? Here's another instance of I presented things using proportionalities, but you don't get to put in numbers if there's a proportionality. But I asked for numbers, so you got to have a relationship that doesn't depend on that, so we use this graph. And so this is straightforward, you just take it off the graph. So you get log of this is on the horizontal axis, so you pick up the absolute brightness with one of these. They all give you the same basic answer. So if we're trying to do precision astronomy, then you want to actually do the error propagation. I don't feel like getting into all that. So we'll just pick one of these, and I think I has the tightest spread. So you get a log of this that's like 2.2, so you get an absolute brightness that's like 18 or 19. And then what do? So now that I have the absolute brightness, how do I find the distance?
Distance modulus.
I use the distance modulus. So I gave you the apparent brightness, and then the distance modulus. U equals little m minus big M equals minus 5 log d over 10 parsecs. And then you just stick it into here and do a little dot algebra.
I like that method better.
Was that?
I like that method better.
How did you do?
I did that. Well, I'll talk to you about it. You said I shouldn't do it because this is the way you set it up for. But you could just, since you have the velocity, you can just use the Hubble's constant and get around it. But
yeah, also true is if you just take this 800, this is the mean velocity of the galaxy. So I can use Hubble law and I get the same answer, which is nice. I didn't know that this was going to work until you actually pointed that out.
it's like slightly off, but it later compared to like the two different answers, but you get pretty close.
Oh yeah, I mean, we didn't do any error propagation. They have no reason to be off, to be anywhere close to each other. So, I mean, if you actually want to do this properly and get numbers that are close to each other, then you got to carefully take care of the errors here and follow the errors all the way through. Yeah.
So on those graphs on the right, the x-axis is the log of the Vmax.
Yeah.
The velocity towards us.
Yeah.
Or away from us.
Yes, that's right.
Okay.
It's really the log of the width of the curve over 2 sin I. But it's the same. But the 2 sin I takes care of everything else. Vmax is the thing that we want.
Yeah. Okay.
Any other questions on this one? Yeah.
Sorry, how did you pick out of the 4 line graphs?
Well, so they're all basically the same. So we just pick I for because I got to pick one of them.
Okay.
It's the tightest. So it doesn't make a ton of difference which one you use. So then what you do is you take the log of that, you find it on here, and then you just draw a line up and find out what the apparent brightness is. That one was number. Am I on order yet? Nope. Boop, 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 boop. Okay. Star formation rate of 50 solar masses per year. What's the measured H alpha flux? It's just this math. So you should get 6.2 times 10 to the 42 ergs per second. You just drop 50 into there and multiply by this other number. It's really straightforward. What kind of stars are responsible for all of this flux? O stars, the big fat O stars. Why are they responsible? I mean, what is the O star doing that is making the H alpha flux?
Releasing UV photons.
Was that?
Releasing UV photons.
Right, UV photons, which ionize the hydrogen, and then the hydrogen recombines and gives me my H alpha. And why are they good indicators of star formation?
They're going to be the shortest lived.
Because they're the shortest lived, because they live basically instantaneously. So if I see massive stars, I know that the star formation is going on right now. And I know how long it has been going on because star formations don't last very long. I just realized that my answers have this dumb typo in them. Anyway. Because what we're looking for is delta M over delta T as delta T goes to 0. This is what M dot is. That's the actual derivative. So we want delta T to be short. We want delta M to be small too, and so fortunately O stars only measure a small fraction of the stars. Okay. La 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 la. M80 is a globular cluster with a mass of 5 times 10 to the 5 solar masses and a radius of 14 parsecs and a velocity dispersion of 12 kilometers per second. Is this relaxed? What'd you say? Who's on team yes? Who's on team no, it's not relaxed? Okay, so it depends on how you get the answer, you get a different answer. So if you say, so the answer is actually a little bit more complicated than just yes or no. The answer is yes, but it didn't do it that way. So we talked about 2 things. We talked about virial theorem. Virial theorem says that sigma squared equals gm over r. And so the quickest thing to do is to say sigma equals 12.4 kilometers per second, and the square root of gm over r equals, you get 12.1 kilometers per second if you did it that way. It's basically the same. So you can say, using the virial theorem, that this is a virialized object. So it is reasonably relaxed. The other way you can do this is the 2-body relaxation time. And I gave full credit with it, whichever answer you got. I think they're both legitimate solutions to the question. It's just a little bit more nuance. Maybe I actually need to rewrite the questions so that we bring out all that nuance. The 2-body relaxation time scale. The time scale is the crossing time times the number of particles divided by the log of the number of particles. So to do it this way, you've got to figure out what the number of particles is. And I said that the mass is 5 times 10 to the 5 solar masses. So how many stars is probably in that? A couple of you said 10 to the 12, which If I divide 5 times 10 to the 5 solar masses by 10 to the 12, I get about 10 Earth masses. Far, far, far too many. An Earth mass is not a star. You can't have a globular cluster of Earths. But if you say that one is typically like 1 solar mass and you get this many stars, that's a pretty reasonable approximation. So T cross is going to be 14 parsecs divided by 12 kilometers per second times 5 times 10 to the 5 over the log of 5 times 10 to the 5, which is 5. And this gives you like 1,000,000 years, which isn't very long, but this is a big number. So now we suddenly have something that's way longer than the age of the universe by a couple hundred billion years. So this says that it's not relaxed. So the real answer is it is a relaxed object, but it didn't do it this way. It formed from a more violent process that formed everything all at once. So I gave full credit for either answer. I think either answer is good. I'll ask a little bit less vague question. Yeah.
I was wondering, what if we use like n equals 5 times 10 to the 4 stars?
Also fine. That's a bunch of big stars.
Yeah.
And then do you get something that's relaxed?
Something that's like relaxed.
So you get something that's relaxed, but those are all 10 solar mass stars.
Yeah.
Having 1,000,000 10 solar mass stars is pretty rare, so that's a rare thing. But I gave full credit for that. Yeah.
So you got T cross by doing the radius divided by the velocity dispersion?
Yeah.
Okay.
Or the diameter divided by the velocity dispersion. Maybe I said radius. It's within a factor of 2. I don't care.
Okay.
Yeah.
Would it be more possible for like that many like 10 solar mass stars if this was like, I don't know, a couple billion years ago?
No, making them into this shape is the hard part.
Okay.
Getting that many in that shape, they still don't last very long. So they all blow up. Because a 10 solar mass star only lives for a couple million years. So the problem gets worse. A better number would be like 0.75 solar masses, which makes this problem worse because this number gets bigger by 3/4. The typical star, if you're just looking at a field of stars, the typical star is a little bit less than a solar mass. But anyway, I liked all of your answers. So even if what I said was different, I might have complained if you used 10 to the 12 because that's far too many stars. But other than that, I think everybody did a great job. Okay, studying a single stellar population from birth to 13 gigayears. Here's another one that everybody did a little wrong. And it took me a minute to sort out why, and then I realized that everybody was missing a minus sign. You're all missing a minus sign in your color. Because color works like a magnitude, and there's a minus sign. I'll show you where it is and where it tripped everybody up in a second. So let's start off. Let's pull up the thing. Can I get them both on one spot? No. So here is our graphic. Let's see. I want to pull both things up at once. Bear with me 1 second. I gotta be obnoxious. Here's the plot, and here are my questions. I can't get to the corner. I made it too big. What are my actual questions that I asked? Oh yeah, I forgot there's that one too. Okay, what stars dominate the spectrum at 1 mega year? Oops. Which is this curve here. So those are big O and B stars. What kind of telescope do I need to see that peak? A UV telescope, because that's the UV. So what happens between this line and this line to make this thing deflate so hard and puff up over here? Right. So this is O stars leaving the main sequence and joining the giant branch sequences. So they get less blue and more red because they get cooler and bigger and brighter. Look up the SDSS UGrids filters. I got 3,500 angstroms and 7,000 angstroms for those two, which are 1, 2, 3 here, just inside the 4,000 angstrom break. Actually, in retrospect, it's not a good line to use because it's south of the 4,000 angstrom break. I should use a longer line, but it doesn't change anybody's results. So the last bit is sketch U minus I color as a function of time. And I want to make a bunch of connections on this because there are several things that we want to connect. So what do we see? Oh, can I put lines on that thing here? I can do that, right? Perfect. 1, 2, 3.5. Like there. I get another one. Like 7,000 here. Okay, I'm just gonna snug this inside the 4,000 angstrom break, just because that break makes things a little trickier. But it doesn't change the answer. So what is the slope of this? So the one on the left is U and the one on the right is I, right? So would you classify the slope of this as this first line here? Actually, yeah, it doesn't matter. Let's use this, the 1 in a million. Is that a positive or a negative slope? It's a negative slope. So U minus I is going to be a positive number because I minus U is the slope. U minus I is the backwards of that. But then there's another minus sign. Why is there another minus line? Color is defined yan. So it's just like every other magnitude-y looking thing that we do. It's even in, when you're using distance modulus, there's a minus sign in that distance modulus too. You just can't see it because we take it out and make it look nicer. But when you're doing distance modulus, you have minus 2.5 times the log of the flux over 4 pi d squared. And the squared comes down and makes this a 5, and this is on the bottom, that's a minus sign, so I get a minus 5. So this just becomes log of just d, and then everything else goes away, because d is the only thing I care about. So this minus sign is important, and so what that does is it inverts the thing. So this, u is here and I is here. So I want u minus I, so that's going to give me a positive number, but then they both get, since this is the flux in the vertical axis, they both get a minus sign, so then we actually start off with a negative number down here. And then as we look, as the thing evolves, you can see the slope, formal slope, like you learned in calculus, it starts at pretty negative and gets progressively higher. U minus I starts positive and gets progressively lower, but that minus sign flips it around again. So we should have something like this that goes like that. This is U minus I. But just about everybody, apologize if I missed one, just about everybody drew something like that, which is really what I kind of asked, but not really what I asked. Because this isn't U, this is minus U. And this is minus I, is this value here. So the curve that you want goes like this. And then to error check, population of stars, as it evolves, does it get redder or bluer? Redder, right? This is the theme that we've been on for a long time. So things get redder as they evolve. Is red a big number or a small number? Red or big numbers. When you have a color, smaller number is bluer. So smaller number is bluer. Then galaxies get redder. So you can see just by looking that this is the wrong direction because this is a population that's getting bluer. This is one that's getting redder. So relatively innocuous problem, but the minus sign is important. Does anybody have any questions about that one? Anybody have any questions about? I think that's it for this one. Yeah. Oh no, the genes length. Forgot about the genes length question. How am I doing on time? It's 12:50. I'm going to go through this kind of quick because I think everybody got this one. Stop me if you want me to do it slow, but I'll do it just for completeness. So we want a blob. We want to find what the gene's length is. And I swear I had changed the problem before I uploaded it, but apparently I didn't. So in my head, I asked for the gene's mass too. Keep the gene's mass in your head. So the gene's length is what? Okay, so the sound crossing time, T cross, is just going to be L over V. And I think actually there's an error in my notes. The solutions are wrong. So sorry about that. There are some errors in the solution because I always write those in a hurry. So if you come across one, just email me and say, hey, is this wrong? Because odds are it's right. Odds are you are correct. T cross is L over V. T free fall, you work through those dimensions. You got a G, you got a rho. We raise them both to these powers. And we get that T free fall is G rho to the 1 minus 1/2. So the biggest thing that you can get is going to be when T cross is smaller than T free fall, and this gives you just C sound over square root of G rho. I think everybody got that one right. Somebody want to talk about that in any way? So simplify in your head. So there's all these numbers out front. They matter. I don't want to say that the numbers don't matter. But C sound and square root of G rho, or square root of temperature and square root of G rho, is the way to think about this. Okay. Any other questions on star formation and galaxy evolution? Let us talk about cosmology. So starting from that, we'll just write this up over here because we'll need it. We have A dot over A squared equals H naught squared times omega radiation, A to the minus 4, plus omega matter, A to the minus 3, plus a thing that's 0, plus omega lambda. The only reason I put that 0 in is because the book includes this term. So that term, this other term, is proportional to 1 minus omega matter minus omega lambda, which is 1 minus 0.3 minus 0.7, which is equal to 0. So we've measured this term to not matter, so I throw it out all the time. Doesn't matter. What it represents is the extra curvature in all of the random space that's out there. So space has stiffness. So if I bend it, I put energy into the bending. Does that make sense? And then that energy matters. So, for instance, if I'm the sun and I have Mercury, Mercury doesn't see just a 1 over r squared potential. It seems a little stiffer potential than that. There's a little bit more energy that Mercury sees, so it goes a little quicker than it would otherwise. Curvature has energy too, but on average, there isn't any in the universe. Does that make sense? So lots of little spots where there's a big curvature energy around planets, around black holes, around you and me. But on average, over the whole universe, it's 0. So that term goes away. So, starting from that, prove that in an Einstein de Sitter universe, A goes like 3h0 over 2t to the 3 halves. What's Einstein de Sitter? Omega m equals 1 and omega lambda equals 0. So the total is 1, and that's the important bit about the Einstein de Sitter universe is the total is 1.
And omega r is also 0.
And omega r is 0. Which is, omega r is basically 0 anyway, for most of the history of the universe.
I forgot to do that, so my thing got like a whole page, like really long, like halfway through, I'm like, oh yeah, this is also 0.
You try to do it with 2 terms.
Yeah, I'm like, this is not gonna work. And it's like, oh, okay.
Yeah, so you very quickly with this equation, you get into something that you have to numerically solve. You can't integrate that. Okay, so EDS says that omega matter equals 1 and omega lambda equals 0. We're all happy with what omega matter means before I go too far. So this is the energy density in mass, all the gravitating things, divided by the critical density of the universe. So it's 1, so we're at the critical density. So we start off with this equation and we get A dot over A squared equals H naught squared. We're in Einstein de Sitter, so that first term goes away. The second term is omega matter, which equals 1, A to the minus 3, and then the other term goes away. So we take a square root and we're left with A dot, actually let's do math first. A dot squared equals H naught squared. Let's get rid of that 1. A to the minus 3 times A to the minus 2 gives me A to the minus, no, A to the 2 gives me A to the minus 1. And when I screw up, feel free to holler out. So we take a square root and we got A dot equals H naught squared A to the minus 1/2. This guy comes over here and the dt goes over there and we're left with dA times A to the 1/2 equals H naught, oh, that's not squared anymore. Oh, that was squared. Here's not squared. H naught not squared. Dt. So I get a 3/2 A to the 3/2 equals H naught T. Two-thirds. Two-thirds, I know how to do that. So the 2/3 goes over there and the 3/2. And you're left with A equals H naught. 3/2 H naught T to the 2/3. Are we happy? So the next one says do the same thing, but show that it goes like the square root. So the only difference is now that's not 1 anymore, and this is an R. And this is a 4. And then I can't keep any of that. Kind of a bummer. So let's do again. We got A dot squared equals H naught squared omega R A to the minus 2. A dot equals H naught omega R to the 1/2 A. I did this like 5 times in a row this morning when I was sitting down doing this problem to make sure that it did what I was supposed to do, and I kept screwing up this -1, and I kept getting a log. I'm like, why is this log? Because I can't do that. Don't screw up your minus signs. -1. Minus signs are the worst thing to screw up when you're doing math. 2s are the best thing to screw up because it doesn't matter if you're off by a factor of 2, but if you're off by a minus sign, the whole behavior changes. So okay, A comes over here, and we got A dA equals H naught omega R to the 1/2 dt, and then this becomes 1 half A squared equals H naught omega R 1 half T A equals H naught omega R 1 half T O 2 to the 1 half. Good. Everybody happy with that? Compute in years the time at which matter and radiation become equal, assuming expansion is dominated by radiation for the entire time. So matter radiation equality happens when omega r at omega r over omega m. Why is that? What does matter radiation equality mean? It means the energy densities are the same. So E of Q is going to be omega Q A to the Q, whatever Q happens to be. So all my energies look like that, because the energy densities do this. So we say that E radiation equals E matter. That means that omega radiation A to the minus 4 equals omega matter A to the minus 3. So we just solve for A, and we get that A equals omega radiation over omega matter. So the scale factor that this happens at is whatever this ratio is. And we look this up, and this is 4 times 10 to the minus 5 over h squared 1 over omega matter. This is omega radiation, and this is omega matter. And this h, the book never talks about it, but it starts to use it because that's how science goes. Sometimes you just got to start talking about something. This little h, I'm just going to go through it again real quick. What does this little h mean? So h naught is little h times 100. Actually, let's rewrite this. H naught is little h times 100 megaparsecs, or 100 kilometers per second per megaparsec. The reason that we have this little h is so that we can pack all our ignorance into one little nugget, and then we can unpack our ignorance as we need to. We can tweak the system based on what we know as our knowledge changes. So a megaparsec, nothing's a million light years away without being found by the cosmological expansion. That's not true, but basically everything is found by the cosmological expansion. We don't really know what h naught is until we've measured it. 100 is a pretty good guess. It's not right, but it's a pretty good guess. So we take care of little h to be how wrong from that is. So if h naught is actually 70, then what is little h? 0.7. So the little h, if you just call it 1 in everything that you're doing, I'm not going to mark that wrong because that's totally fine. That's a cosmology that might exist. It's better to use 0.7 or maybe 0.68 or maybe 0.72. I'm not sure which one of those it is. So little h is going to be like 0.7. Yeah, so okay, that's A. And then we just need to say A equals A equality equals, oh, I erased it. 2 h naught omega radiation to the 1 half t to the square root. So this is the equation that I found in the last one, right? I have it here again. So this is now we're using this A equality here, and we're using this, which is missing from the notes. There's an omega radiation to the 1 half that should be in this solution. That I'm not sure how I have assigned this problem several times and not noticed that, but there you go. Or it's possible that I notice every time and I'm like, shit, I should fix that, and then I don't fix it. It's also possible. So how do we solve this? So this is just A equality is omega r over omega m equals, let's square that, and we'll divide by an omega r to the 1 half, so, and a 2 and an h naught, and that gives us a t. Is that everything? Yeah, that's everything. Then you plug in numbers. Omega r is this. Omega matter is 0.3. So you plug in 10 to the minus 5, 10 to the minus 5, 0.3, and you should get something. I got 89,000 years, which is actually longer than I thought it was by a little bit. A better value is 47,000 years. That's what happens if you keep both terms in the evolution equation. But somewhere between, this is what I said before, somewhere between 5 million and a half million years, between 5 minutes and a half million years. Logarithmically, that's like 70,000, right? What redshift do the matter and dark energy densities equal each other? We do this one, yeah.
So let's say that question's on the exam. So as long as you can get that, like, you would get like
I care about process more than answers.
Okay.
So as long as you do something that makes sense and show me that you do something that makes sense, I kind of don't care about what the answer is, as long as it's not older than the age of the universe or faster than the speed of light. As long as it's not obviously falsifiable by very simple things, then I kind of don't care about what the numbers are. That being said, sometimes on the final, how big is the Milky Way is a question that might show up. So sometimes I do care about the numbers, but process is really what I care more about. But that's a good question. Okay, at what redshift does dark matter and dark energies equal each other? We do the same stunt we did here. Except we say that omega matter, a to the minus 3 equals omega lambda all by itself. So this is 0.7, this is 0.3, and a goes over there, this guy comes over here, I get omega matter over omega lambda to the 1/3 equals a EQ. That's the equality scale factor that we want. And then the redshift is 1 over 1 plus a. Is that right? Now I have to rewrite. Was that? Oh, third. Yeah, thanks. Should be to the third power because we got a third power here. And then you get redshift from that, and you should get a redshift. It's right there. Z is 1 over a minus 1. Not what I just wrote down because my brain has provided the wrong thing. And you should get a redshift of about 0.32, which was when the universe was smaller, but not a ton smaller. You have a question?
Sorry.
Okay, no worries. Okay. So the Davon is a particle I made up that has a mass of 20% of the proton. At what temperature does it decouple from the radiation? So there, the simplest approximation you can make is just that the kT, the energy at the temperature, has got to be able to make the particle. So kT has got to be bigger than the mass of the Davon times c squared, which is 0.2 times the mass of the proton times c squared over the Boltzmann constant, which should give you about 10 to the 12 Kelvin, which is a large number, but this is astrophysics. You're allowed to have large numbers. There really aren't very many things in the universe that get that hot, to be perfectly honest. Even supernova are a factor of 1,000 times cooler than that. Okay, this translates to a scale factor. How do you find that? Temperature goes down like A. So T is the temperature now, which is what? What's the temperature? 2.7 divided by A, so you just shuffle that around. And you get a scale factor of 10 to the minus 12, which is much smaller than 10 to the minus 4 that matter radiation equality is. And that's a number in the book. Questions on that? Good. The first star is formed at a redshift of about 19. JWST is starting to see this. Like, that's almost what we can see. We can almost see these things. So what scale factor does that translate to?
It's
1 over 20. How much denser is the universe on average? Yeah. 1 over a cubed. So that's just 20 cubed. How much hotter is it? 20 times hotter. So should get a value of about 3,000 for that. No, not. That's the other question. You get a value of whatever 20 times 2 is like 50, 57. Yeah. It's right here. 52. There you go. There you go. And then the last bit is how much larger is the gene's mass at this redshift using the mean temperature and density versus the red gene's mass now using the mean temperature and density. So here's a quantity that weirdly doesn't change at all, but the fact that it doesn't change actually doesn't matter. It's just kind of a curious coincidence. So the gene's mass is C sound cubed over G rho, square root of G rho. Equals the temperature to the 3 halves over G rho. So remember the sound speed is the square root of the temperature. And there's a K and a mass of the proton in there to make everything make sense. But really, we should have proportionalities on these, especially on this one, because I definitely did throw out a K Boltzmann. So, the gene's mass at Z over the gene's mass at a redshift of 0 is going to be T at Z over G cancels, square root of rho at Z over T naught over square root of rho naught. Right? This is equal to T over A, T naught over A to the 3 halves over rho naught over A cubed to the 1 half over T naught to the 3 halves over rho naught to the 1 half. So this cancels this, and this cancels this, and this cancels this, because that's 3, 2, and this is 1, 3 halves. All my A's cancel out, and I'm just left with 1. So the gene's mass of the mean universe doesn't evolve. That doesn't actually say anything for the star formation. It's just a curious fact, because the temperature goes up, but so does the density. All right, let's talk about the CMB. What's the CMB stand for? What temperature is the CMB at a redshift of 0? 2.7, that's the universe. At what redshift do we see the CMB? Where do those red photons originate? At 1100. What temperature is that? That's the 3000 squirrel brain was trying to give me a minute ago. What is the shape of the CMB spectrum? It is a black body. What causes the fluctuations to occur? So it's a black body plus little tiny sound waves. Little tiny sound waves, how big are, so what are, I just guess said it. It's little tiny fluctuations. What makes those little tiny fluctuations? Sound waves in the early universe. Are we happy with that, or is people confused by that?
Is it like a pressure wave in space? So it's just like density kind of goes up in some spaces and then just
Yeah.
kind of makes it go everywhere.
Yeah, density goes up in some spaces and down in other spaces. And as the density goes up, the pressure goes up and the temperature goes up. So you get a little hotter spot. So if you plotted a black body at each little point, some black bodies would be shifted relative to other ones. Not very much. How large are the fluctuations? They're like a millikelvin, like 10 to the minus 6 Kelvin. And then the last one. The universe is opaque before the CMB and transparent after. What causes the universe to become transparent? Recombination. Recombination. So this is the electrons all find the protons and form neutral hydrogen for the first time. And when everything is charged, the photons can't go very far because a photon just scatters right off of a free electron. Oops, I'm on the wrong screen. There we go. And is that it for homeworks? That's it. Okay. Anybody have any questions on homeworks? Anybody have any questions on? Does anybody have any questions on things to study for the midterm? Yeah.
Did you check if they have like a change?
Oh, sure. Yeah. Was that?
Your calculator's on the midterm, right?
Yes. Okay. So, thank you. Calculator. Bring a calculator. I don't know. I haven't written it yet, so I don't actually know if there's any calculator problems on there. But there's a good bet that there will be. So bring a calculator. And an 8.5 by 11. So an 8.5 by 11 sheet of your favorite equations, or pictures of stuff, whatever. Yeah,
Is it just one side or?
you use both sides.
Will that also like include equation or like equations, constants, or would we get a constants?
I'm not going to give you anything here.
Okay, so
So,
all the constants are on.
Yeah. So you probably want to write down Planck's constant, but I don't know. I might give you Planck's constant. So like Planck's constant in G, I'll probably give you. So basic physics constants, and then like if for whatever reason you need a constant that you don't have, you can ask. That's not a big deal. But you know, pictures of galaxies, or Hubble's tuning fork, or all kinds of stuff. Gene's mass, lots of things. Okay, tangent point method. So the basic idea of the tangent point method. Sorry, is there any other like structural questions? Should be in here on Thursday, unless you're taking it at the testing center, in which case it'll be there on Thursday. Okay, tangent point method. So we are in this galaxy. Here we are, nice and smiling. Now when I look, so here's the galaxy that I'm looking at. And I'm going to point my telescope at a point, some galactic longitude, L. And I'm just going to like measure from Sagittarius to the left or to the right along the ecliptic. So I'm just going to point my telescope at this angle, L. So that's looking like this. And I'm going to take a radio measurement of everything along that line of sight. Now along that line of sight, here's the galactic center. Here are some fictitious curves that I'm drawing. These are different radii at which stuff exists. So throughout the galaxy, there are clouds of carbon monoxide. Carbon monoxide is the second most abundant molecule in the universe. The first being molecular hydrogen. I think water is the third, which is why there's so much water. Maybe it's like 10, but it's very high up there. So clouds of carbon monoxide. Carbon monoxide is nice because you can see it in the radio. So when I point my telescope out along this line of sight, I pick up a bunch of clouds. There's this cloud, this cloud, this cloud, and this cloud. They're all moving at different velocities. Different velocities. So they have two different velocities. So each cloud has a v tangential of r, and this goes like 1 over r. It's a decreasing function. It doesn't actually go like 1 over r when you get very far out, because then it starts to get flat. Galactic rotation curves get flat. And there's the v line of sight of r, which is vt times the cosine of the angle between the radius, between the tangent and me. It's cosine, right? When that goes to 0, that goes to 1, right? So when I make my radio map, yes,
Where is the angle exactly?
the angle is between. So this thing is this cloud here is moving with this velocity because it's on a circle. I'm not viewing this velocity. I'm viewing this velocity. So here is the tangent, and here is the line of sight, and this angle downweights the velocity that I measure for this cloud. So the velocity that I measure for this cloud is going to be its circular velocity times the cosine of the angle between between its velocity and where I'm looking. So if it's looking like this, so if I'm looking at it and it's perpendicular to me, I'm going to measure a velocity of 0. So if I look this way, straight in toward the center, when I look at this cloud, I get a velocity of 0 because it's not along the line of sight. But this one here, where my line of sight is tangent to the circle, I have all of the velocity. So the tangent point method gives you the maximum velocity on one of these clouds for two reasons. One of these clouds is furthest in, simultaneously closest to Sagittarius, so closest to the center of the galaxy, and 2, along the line of sight. So when I measure the projected velocity of each of these clouds, I get different velocities. This is a spectrum as a function of wavelength. We can make it a spectrum as a function of velocity instead. Perfectly fine. Velocity and wavelength are related by the Doppler shift. So this fastest cloud, so this guy up here, I get its position and its velocity by the fact that it's the fastest thing. It's the fastest cloud that I measure. Being the fastest cloud that I measure, I know two things. I know that it is the closest to the Sagittarius star, and I know that it is tangent to it, that its velocity is tangent to the line of sight. So I see all the velocity. So that gives me the velocity of everything moving on this curve. So I just need to do that so I can get the velocity of this radius by measuring along this line and just looking at the fastest thing along that line. And then if I want this radius, so if I run a radius, cartoon space. So if I'm looking at a galactic longitude of L along the line of sight, then the fastest thing is going to be at a radius of, this is R naught, that's like 8.5 kiloparsecs, okay, 8 kiloparsecs. So it's going to be this radius, R star is R naught times cosine of L. And V star is the fastest thing I measure. And it works to give me the cloud that's at this point by the geometry, by the tangent. That make sense? I'm not going to ask you to actually recreate it. So don't you don't need to actually rebuild anything in this. I might ask you some kind of general questions, but there wasn't a lot on the homeworks on that detail, so you don't need to go too deep down that rabbit hole. So I have 0 minutes left, right? I ended now, right? So let me give you the nickel tour of what to study. Go through all the homeworks, make sure you can do all of them. I don't think there's anything on the homework that I wouldn't put on the test. There weren't any super long derivations, and all the medium-sized derivations are things that I would put on the test. So Go through the homeworks. That's the most important thing. And then second, once you've gone through all the homeworks and you're comfortable with everything that I've asked, then go through the slides and make sure there's nothing else that I talked about a bunch. So anything that comes up more than once, you should make sure you look at. So anybody have any other questions? I don't mind talking for another minute if you guys have other things that are burning in your mind that you want to talk about before we part ways. Yeah.
This is really nitpicky, but the thing that was like the singular isothermal sphere question, does that count as a long derivation that wouldn't be on the test? Because that was the one we like used the test just for.
I would feed you. I would feed it to you. I wouldn't ask you to remember that first part. So I might give you that. That's a good question. But showing that a 1 over r squared density profile satisfies the equilibrium is something that I might ask. So go through it and make sure you understand it. It's not. It is longer, but it might show it. So make sure you go through that one. Anything else? Everybody good? See you Thursday. Sorry I didn't get much in the way of midterm review, but really the midterm review is just going to be, I go through the homeworks and say, you should know how to do this problem, and this problem, and this problem, and this problem, and this problem. So just pretend I'm doing that. Yeah.
How many questions?
I haven't written it yet. I don't know. 4 or 5. But you only have an hour, so I'm going to ask you an hour's worth of questions. Yeah.
On my 43, you gave me a 38 out of 0, so I have like 115 in class.
Oh.
That's right. I just wanted to give you
Oh yeah, I should look into that. I haven't sanitized the grade book yet,
Okay,
but let
yeah,
me.
just wanted to-
Let's see what I did.
I think it's like 1,000% or something.
That's awesome. Why?
It's all good. Whenever you get around to it.
I know, I saw that.
If I do it right now, then I remember though. Oh, because you didn't like the browser. Yeah.
Possible to be office hours tomorrow, so like in case I have extra questions.
Yeah. How many people want office hours tomorrow? All right. Cool. Yeah.
I'm down for it.
Yeah. Is 4 o'clock okay?
Yeah, that's good.
Okay. All right. Yeah. I'll just show up if I forget an announcement. If you could actually email me that question, then I'll make an announcement to everybody.
Okay.
Yeah. Grades. Yeah. See you guys. How are you doing?
How did you get to it? Good. How about you?
Not too bad. Yeah, everybody's got 120%. Dope. I'll fix that. That's hilarious. So how are you doing? Where are you at?
Good. Well, not so good in the sense that I'm behind, but I am working on catching up on anything. I was doing some of the reading
Okay.